What I would like to do now is build a machine learning model to, you know, see how well we can do with predicting this data set. So there's some different options that we could try. First, note that this is the big question. Okay, is this a regression or classification data set? Let's take a look at the y value counts. Okay, go ahead and enter this in. Enter y, right? So that's what we're trying to predict. Dot value underscore counts, followed by parentheses, and press Shift Enter. And what this does is it shows the number of values of between 0 and 9 of the different cases. Now, this is a little bit tricky almost because the question is this regression or classification? Like, is this quantifiable? Well, these are handwritten digits, right? It is not the case that 9 is closer to 8, say, than it is to 7 here. Why? Because it's not the value that matters, it's the shape, it's the image. So in effect, this is a classification problem. We want to classify images into these different bins, these different numbers. Okay, so this does fit then logistic regression and different classifiers. Okay, let's take a look first at how to do it with, say, logistic regression. Okay, we've got our X and Y ready. We can go ahead and do it. So code with me. From sklearn.linear model, import logistic regression. And then what we want to do is we want to actually go ahead and set up a model. So model equals logistic regression. Now we have to make a couple changes here, okay? So just set max iter to 5,000, okay? If you don't do that, it'll likely won't converge, okay? Just like the epochs, like the number of iterations. And then here's the thing you have to do. Multi-class, multi-underscore class equals multinomial. Why? Well, logistic regression by default is a binary, right? Machine learning algorithm. You solve it with the zeros and ones. So you have to make a specification so that it knows to actually split it into multiple classes. And then it can figure out that there's going to be 10 on its own. So from there, we can do it like regular model.fit X and Y. Now, I want to do both. I want to show the score of X and Y. By the way, I want to do this a little differently. I want to show you how to get your outputs just a little bit nicer. So training score equals model.score X comma Y. I'll just call it the train score, shorten it a little bit. Excuse me. And then I also want to do a test score. Okay. Why am I doing this? Because I want to see if it's overfitting. And that's how we would know. So model.score X test, Y test. And so can you figure out what is going to basically reveal that? Right? How are you going to, like, what kind of difference would show that it's overfitting? Well, if the training score is better than the test score, it's overfitting. I mean, if they're close, it's not, but if it's substantial. So we're going to print, I want to show you F strings if you haven't seen them before. You write an F string training score, and then in curly brackets, you can put in train score. Okay, looks weird if you've never done an F string before, but what this basically does is a convenient way to display strings, right? You just put an F in front of it. And then what's convenient about it? It's actually the squigglies, okay? Because what it does when you put inside of squiggly brackets, it converts it for you, and that's nice, especially when there's a lot of variables. Okay, so I end up using a lot of F strings. Okay, I think that'll work. Let's go ahead and give it a try. Let's see if we get any errors. It's working. You can see it's going to take a little bit to fit here. Cool, right? So what does this reveal? It reveals some interesting things. It reveals that we got a good actually test score, right? 90% were correct, but also reveals that it is overfitting because the training score is perfect. So that could be modified. But let's also do this with the XGBoost classifier, okay? So from XGBoost So I'm going to do another one. Import XGB classifier, model equals XGB classifier. It is more intelligent. You don't have to specify anything. It'll figure it out. And then I'm going to copy the rest of this. Right? It's all the same after you reestablish the model, which is why a function is good. I'm only going to do these two, so I'm not actually going to write a function for this. And then let's run this. Okay. That's going to take a little bit longer to run. Why? Because recall that XGBoost is actually 100 decision trees. So in fact, it takes 100 times as long as like one decision tree. That's why I really shortened this data set so that we're not just sitting here waiting for a long time. But it can be fun to go back on your own. You can change it in rows. You can put in different numbers. You can try the whole data set and see how long it takes and how well it does. Okay. Now, like, let's just, is it going to overfit? I don't know. I mean, if we assume that it does, though, like, you can change max depth. XGBoost has a lot of hyperparameters. Okay, so my results are in. Yours might still be computing. And I got a training score of, again, perfect 1.0, test score of 91% rounding, a little better than logistic regression, but not by much. So it is clearly overfitting. So just to show you, I mean, we could copy it all again. And, if I lower max depth, okay, start typing max depth. Oh, in case you ever wonder like what the default is, here's something cool that you can do. Just type in model, right? So model, should this be? Well, it's an XGBoost because it's fit on the data and initializes an XGB classifier. So if you type in model and press Shift Enter, look, it shows you the defaults. Oh, interesting. So sometimes Colab has their own, or sklearn has their own defaults. I think they lowered the max step. So the default max step is actually 3 here. Okay, that's how deep the trees are. But we could try to lower it to 2. And again, games of 20 questions, right? Think about this. The more questions you ask, the more variance in your data, like the more potential there is for overfitting. So to reduce overfitting, you would actually lower max depth. And in effect, that's all you really need to know about the hyperparameters is you need to know their ranges and which way reduces overfitting. This is not a class in XGBoost. If for anybody in here, if you're interested, I wrote, I believe, the first book on XGBoost in print. You can look it up on Amazon if you just type in XGBoost, and you should see it. So let's change max depth here to maybe 2. Let's see what happens, okay? Give it a whirl. In case you're wondering about some of these other ones that you could try, all these call samples, if those are between 0 and 1, if you drop them from 1, like 0.8, it'll also do this, meaning it's going to help reduce overfitting because they are percentages. And instead of like selecting between, say, all of the samples, it is only going to look at like 80% of them. Okay, same thing with the trees. And so this is interesting. Very interesting, okay. It didn't overfit as much, but the model did not improve. The test score actually went down a little. So yeah, it reduced overfitting, but at the cost of a higher bias. So this is not better, right? I'm going to try one more change. I mentioned about some of those call samples. So if I'll ignore max depth. Let's just try one of these call sample by level. And so let's just try like 0.8. That's not a big difference, but it could be helpful. In fact, let's try another one. Call sample by tree. Let's do by node. Let's also try 0.8 there. Okay, so that's going to reduce overfitting. Because again, instead of selecting between everything, which allows for more variance, more specificity, this is allows for more generalization when you reduce these percentages. I'll just try it. Okay, and then I'm probably going to stop here because, again, the point here is not, hey, how can I master this? It's simply looking at, hey, models are overfitting. It's something we need to address. And now we actually do see how to build machine learning models for the MNIST dataset, which is an image, by the way, and what kind of scores we get. So you can do it without deep learning, but now look at that. Isn't that interesting? It's still overfit, but the test score improved. So it overfit by less, but it wasn't more bias. So you can see how this can become an intricate little game here. And if you want to play around with the XGBoost hyperparameters, again, you can check out my book. You can also check out, if you just type them in, what? Type in XGBoost hyperparameter tuning. I can tell you this analytics vidya is a nice one. Okay. I don't know about this one that shows up first, but they'll go through them, and you want their ranges. Okay, we get pop-ups we don't want. And just to show you really quickly, see, like, they'll tell you about it, like min child weight equals 1, and like you can look at ranges, right? Like look here, max step default 6, that's what I told you, but typical value is 3 to 10. My point is that there's tons of information there if you look. We're going to stop here in this note. Coming up next, we're going to look at how to tackle this data set with deep learning.